Okay, welcome to this explainer. I want to kick things off by asking you a rather weird question. How exactly did a potato salad magically save water? Seriously, think about it for a second. There was this real-life manufacturer of fine foods, and they really wanted to advertise their potato salad as being super environmentally friendly. So they started measuring the energy and water used inside their factory. Well, they quickly realized their potato salad used an absolute ton of water. Why? Because the potatoes arrived covered in dirt and had to be aggressively washed. But then, seemingly overnight, the water usage for this potato salad just plummeted. The environmental burden literally vanished. So how on earth did they pull off this ecological miracle without any new technical innovation? Well, spoiler alert, they didn't invent some magical, high-tech, low-water washing machine. They simply outsourced the potato washing to another enterprise. That's it. The actual water usage out there in the real world didn't drop at all. The company just moved the dirty work off-site. And because they were only looking at what happens strictly inside their own facility, the environmental costs completely disappeared from their own records. It was a total illusion. So how did they get away with this? It happens because of a method called gate-to-gate analysis. This is an operational input-output analysis where the boundaries are drawn strictly at the factory fence. It literally only measures what comes in the front gate and what goes out the back gate. It completely ignores the manufacturing of pre-products, the ultimate waste management, and, as we just saw, outsourcing. It creates these pseudo-improvements. And this, right here, is exactly why we absolutely must have a better, much more holistic way to measure the true environmental impact of the things we produce.
And that brings us to the actual core of today's explainer, life cycle assessment, or LCA. This is the internationally standardized method we use to track the true systemic ecological cost of a product, cutting right through those illusions and getting down to the reality of green. Section 1. Defining life cycle assessment. Let's dive right in and see how international standards actually solve that potato salad problem. According to the official ISO standard, a life cycle assessment studies the environmental aspects and potential impacts throughout a product's life. The absolutely crucial phrase to remember here is cradle to grave. This process tracks everything from the initial raw material acquisition all the way through production, the actual use phase by the consumer, and finally disposal. So the core mindset is cradle to grave. We are forcing ourselves to expand our vision way beyond that factory fence.
If you map this out, it makes a lot of sense. Instead of just zooming in on the production of end product phase, which is exactly where our potato salad manufacturer was hiding, LCA forces us to track a product right from the very top. We're talking raw material extraction, including all the energy carriers. Then it tracks all the transportation in between, down into the use phase, and finally all the way down to the very bottom, end of life, disposal, and recycling.
Now, there is a big caveat here, and we need to be super clear about what LCA does not do. LCA strictly focuses on quantifying ecological impacts. We're talking about things like resource use, human health, and ecological consequences. It deliberately excludes economic and social factors. You might wonder why? Well, it's because the methodology is already incredibly complex. If we forced it to also measure economic and social sustainability on top of everything else, the entire method would just become completely overloaded and unusable.
Moving right along to Section 2, finding the functional unit. Let's see how this concept builds the foundation of any proper assessment.
What's really fascinating about this concept is how it totally flips the way we compare products. Think about beverage packaging for a second. If we want to know whether a glass bottle is better for the environment than a cardboard carton, we don't just compare one bottle to one carton. That wouldn't make sense. We actually have to compare the entire product system required to fulfill the exact same function. In this example, let's say the function is providing 1,000 liters of liquid. To pull that off, you'd need 5,000 small pouches, or 2,000 reusable glass bottles, or 1,000 single-use cartons. We are comparing these entire massive systems against each other.
The source material puts it perfectly. The quantified performance of a product system is the intrinsic standard of comparison. Because we're hyper-focused on the function, like delivering those 1,000 liters, it actually allows us to compare physical, tangible goods with intangible services. As long as they serve the exact same function, you can compare them. It's an incredibly powerful way to look at the world. But as you might guess, this kind of system-wide thinking creates a massive challenge. Section 3, drawing the system boundaries. Let's think about something super simple, like a cotton roll towel dispenser in a public restroom. If we want to fully assess a cotton roll towel, well, first we have to look at the cotton production. But to do its job, the towel has to be washed, right?
So step 2, we add the cleansing process, the water, the detergent. But wait, step 3, washing requires a massive industrial washing machine. Do we include the production of that machine itself? If we do, then step 4, that machine needs steel, and that steel requires mining iron ore out of the earth with heavy machinery, and you can easily see how the spiral is completely out of control.
Because literally every small product eventually links back to the entire global industrial system, we have to draw a line somewhere. We use things called cutoff criteria. We basically have to simplify the system to make the mathematical modeling even possible, while carefully making sure nothing essential is omitted. And this is absolutely crucial for detecting trade-offs. We definitely don't want to seemingly solve an environmental problem in one phase of a product's life, only to accidentally shift that exact same burden to a totally different phase or a different environment entirely.
So where did this incredibly meticulous way of thinking actually come from? Let's get into section 4, the history of LCA.
LCA wasn't just born in a vacuum. It actually came out of a real global resource panic. While you can trace its early roots way back to Patrick Geddes' energy studies in the 1880s, the modern concept really kicked off in 1972. That was the year the famous Limits to Growth report was published, right before the huge 1973 oil crisis. Suddenly, an energy-dependent industrial society felt incredibly vulnerable. This sheer panic made system analysis, resource tracking, and energy auditing absolutely vital. By 1990, organizations began formalizing it, ultimately leading to the international ISO standard in 1997.
During that really critical period in the early 90s, the Society of Environmental Toxicology and Chemistry, or CTAC, laid the foundational groundwork for our modern measurements. Notice how they originally conceptualized it as a triangle. On one side, you have the 1990 version focusing on impact analysis and improvement analysis. Fast forward to 1993, and the language tightened up significantly to impact assessment and improvement assessment, all anchored by a strong center core of goal and scope. This simple triangle literally paved the way for the robust standards we rely on today. Which brings us to our final stop today, Section 5, the 4 phases of LCA. A really huge part of this process is the inventory analysis phase. Just look at the inputs, the energy, the water, the raw materials, all flowing into the product system. Then look at the outputs, the emissions, the wastewater, and of course, the final products. In a proper LCA, scientists have to meticulously document every single one of these inputs and outputs across the entire life cycle of the product. All of that meticulous data then feeds directly into the complete ISO 1440 framework. You've got 4 main parts, goal and scope definition at the top, flowing right down into inventory analysis, then into impact assessment, and running alongside all of them is the interpretation phase. But the absolutely crucial thing to notice here is the arrows. See how they point in both directions? That tells us LCA isn't just a simple straight line, it's an iterative, continuous loop. As you learn more in the inventory phase, you might actually have to go all the way back and adjust your initial goal and scope. But here's the catch. Even with all of this rigorous, highly standardized data, we eventually hit the interpretation phase and run face first into what is called the valuation dilemma. Science is incredible at mapping out the hard data from cradle to grave, but science alone cannot easily weigh completely different types of environmental damage against one another. Eventually, somebody has to pragmatically trade off these different environmental impacts. I'll leave you with a really provocative thought to chew on. What if a product's life cycle analysis shows that it saves a massive amount of energy, but the trade-off is that it creates significantly more acid rain? Which one is actually better? LCA is brilliant at exposing the complete systemic truth behind the products we use. It absolutely ensures we aren't just outsourcing our dirty potatoes. But at the end of the day, deciding what environmental cost is acceptable still relies entirely on our own human values.